Hi students, welcome to my lectures on chemical reaction engineering. In today's lecture, we are going to discuss about the important measurement which is called conversion and second limiting reactant, because the conversion and limiting reactant played very important role in designing a reactor. So, because we target a certain conversion in a reactor, so that is why we have to define the conversion and what are the implications of the conversions. And the second, not every molecule, that means if we have to define a conversion, we have to define based on any one molecule, that is A plus B gives rise to C plus D. Among this A and B are our reactants. So, I have to define my conversion, whether it is 10% reaction, 20% reaction, 30% reaction, 100% reaction. I have to define based on any one of the molecules, either A or B. So, whether we have to consider A to define a conversion or B to define a conversion, that is what the limiting reactant. The one which is limiting the reactant is called limiting reactant, and based on this limiting reactant we have to define the conversion. So, let us go into the topic. Let us discuss about the conversion first. The conversion, that means the percentage of reaction you can think of, and it is defined as XA, moles of A reacted by moles of initial moles of A. For example, let us consider A is our limiting reactant. I have to define the limiting reactant based on the molecule A. A is one of the reactants. So, moles of A reacted by initial moles of A. More is the moles reacted, that means the numerator will be higher. If the numerator is higher, the conversion will be higher. The value, the value of the conversion ranges between 0 and 1. 1 is 100%, 0 is 0%. So, more is the A reacting in a reactor, that means more is the conversion. Less is the A that got reacted in the reactor, less is the conversion. Let us take for example, there is one batch reactor. Initially I have these many molecules, I have 1, 2, 3, 4, 5, 6, 7, 8 molecules of A, and I have conducted the reaction for a certain time period T. After T, the 4 molecules of A is not reacted, that is still remained in the reaction, and 4 molecules of B formed, means 4 molecules of A got reacted to form B. If this is the case, let us define what is initial moles, final moles, moles remained, all these factors. These are initial moles of A, is not denoted by the symbol Na0. Okay? The 1, 2, 3, 4, these are the 4 molecules of or moles of A that is unreacted or remained. That means moles of A unreacted or remained. Okay? And these are the 4 molecules of B has been formed. If 4 molecules of B has been formed, that means if this is the reaction, 4 molecules of A got reacted. That means this means 4 molecules of A got reacted. That is why it is denoted by moles of A reacted to B. This is what has to go in here. Moles of A reacted to B. This is the symbol, this is the things that goes in here. So, let us get this equation. From 1, I know moles of A reacted is equal to XA times initial moles of B. Okay, one second. Initial moles of B. Moles of A reacted is XA times initial moles of A. That means moles of A remained is nothing but, that means how many moles of A remained, that means is nothing but initial moles minus reacted moles. That is what moles that is remained after the reaction. So, that is why moles of A remained, which is denoted by the symbol Na, which is nothing but moles of A minus moles of A reacted. That means initial moles of A minus moles of A reacted. Okay. Let us, Na is moles of A remained, nothing but initial moles of A is denoted by symbol Na0. What is moles of A reacted? Moles of A reacted is XA times initial moles of A. That means XA times Na0. That is Na is nothing but, if you common out the Na0, 1 minus X. That means this is the moles that is remained after the reaction. And if you know, and based on this equation, you can say that how much moles can be, let us say 50% reaction happens. Then tell me how many moles of A that is remained in the reactor. That means simple. If you know Na0 initial moles into 1 minus 50% reaction means X equal to 0.5. Okay, Na0 into 1 minus 0.5, you get how much amount of A remained after the reaction. Similarly, you can measure Na as well as concentrations also. Na denotes moles, Ca denotes concentration. Concentration nothing but mole by volume. Okay. If you know the volume of the reactor, then you have to plug in concentration of A remained after the reaction is nothing but moles of A remained after the reaction divided by volume of the reactor. Na is nothing but Na0 into 1 minus X divided by V. Okay. Na. Okay. Example. Find Na if X is equal to 0.5. That means it is given that if the percentage reaction is 50%, that means conversion is 50%. Tell me how many moles of A that is remained or unreacted. Given initial moles is equal to 1000 moles. A volume of the reactor is, you can say, 1 liter. Na equal to 1000 minus 1 minus 0.5, that is 500 moles. That is, conversion is 50%, means initial moles is 1000. That means out of this 1000, only 50% moles of A got reacted. That means how many moles of A that is remained still in the reactor is nothing but 500 moles, which can be calculated with this equation. Similarly, you can find out the concentrations. What is the final concentration of A remained in the reactor after the reaction? Nothing but Na by V and Na0 into 1 minus X by V. I know volume of the batch reactor, it is 1 liter constant volume batch reactor. If 1000 divided by 1 into 1 minus 0.5, this is 500 mole per liter. That means the concentration of A remained after the reaction is 500 mole per liter. This is what about the conversion. And the second most important topic, which is called, here XA I have to put, okay. Here by default I have taken XA. Okay. Then what is the reason for me to take the limiting reactant? Because here in this reaction only A is my reactant. If more than one reactant is present, A plus B gives rise to C, then among this A and B, which one I have to consider for finding the conversion? Because here XA is written, okay, it is directly XA is written. But in case of more than 2, whether I have to report XA that is based on A or XB or based on B, today I am going to show you very simple formulas, okay, which can help you in interviews or competitive exams. Let us denote the concept of limiting reactant. That is, A plus B gives rise to C plus D. Among this A and B are my reactants. In this A and B, which one is the limiting reactant? I have to define the conversion based on the limiting reactant. If A is my limiting reactant, then I have to define the conversion in terms of A, that is XA. If B is my limiting reactant, then I have to define my conversion in terms of XB. So with the small example, we can do that in a very simple way. In very simple sense, a limiting reactant is the reactant which is less than the stoichiometric requirement. Means in a reactor I have certain moles of A and certain moles of B. These both are my reactants. Okay. I know what is the requirement, because 1A plus 2B gives rise to C plus D. If this is my equation, 1 mole of A plus 2 mole of B gives rise to 1 mole of C with 1 mole of D. For time being, you neglect this products. Okay. That means every 1 mole of A there is requirement of 2 moles of B. That means every 1 mole of A, double the requirement of B is there. This is called stoichiometric ratio. A plus B, B gives rise to C, C plus D, D. A, B, C, D are the stoichiometric coefficients. A equal to 1, B equal to 2, C equal to 1, D equal to 1. If I take the ratio of B by A, that means 2 by 1, which is 2. That means every 1 mole of A, 2 mole of B is required. If this requirement is not met, when the ratio is less than the stoichiometric amount, what is my limiting reactant? If the ratio is greater than the stoichiometric amount, then which one is the limiting reactor we are going to discuss. Let us say in a reactor, I have kept, there is a reactor in which I have kept 1000 moles of A and 1000 moles of B for the reaction. Okay. Let us see among this A or B, which one is the limiting reactant. Moles of B and moles of A in the reactor is nothing but 1000 moles of B divided by 1000 moles of A, which is 1. 1, that means which is less than the stoichiometric requirement. That means every 1 mole of A, only 1 mole of B is present. But I need, for every 1 mole of A, 2 moles of B is required. That means the amount of B is less than the required amount. In such cases, which one is less in the reactor? That is the limiting reactant. But in this case, I mean, the which one is less? The amount of B is less than the amount of A, which is decided by the stoichiometric coefficient. If that is the case, my B is my limiting reactant. The one which consumes first in the reaction is called the limiting reactant. The one which consumes first means which one is less in amount, that will consume first. Okay, that is what the limiting reactant. But this will help you. Okay, the moles of B by moles of A, 1000 by 1000, 1, which is less than the stoichiometric amount. If this stoichiometric ratio, then limiting reactant is B. In the same reactor, if I keep moles of B is 2000 and moles of A is 1000. Later, what is the ratio of 2000 by 1000? That means 2, which is equal to the stoichiometric requirement. That means moles of B by moles of A is same, that is required as per the stoichiometry. In such cases, which is equal to, because this amount is equal to the stoichiometric amount, okay, then limiting reactant can be either A or B, because both are in same proportion. So you can take either A as a limiting reactant or B as a limiting reactant in designing a reactor. And third case, if moles of B by moles of A is 3000 by 1000, okay, that means more is the amount of B compared to the A, that is greater than the stoichiometric requirement ratio. Okay, in such cases, the one which consumes first, the A molecule will consume first, because B in which higher amount, A molecule will be less. So A molecule will be disappear, that means react earlier than B. So if 3 is greater than the stoichiometric amount, okay, B by A, then the limiting reactant is A. Okay, this is the easy, a very simple formula, and to find out which one is the limiting reactant, if you know what is the concentrations of, I mean, this is moles of B by moles of A. Same way you can talk about the concentration of B by concentration of A. And if the concentration of B by concentration of A is the given 1000 mole per liter by 1000 mole per liter, and you can, but anything, that means you can go with the moles or you can go with the concentration ratios. Okay, that is what the concept. Less than B by A, that is B is the limiting reactant. Equal to B by A, that means A and B both can be, anyone can be limiting reactant. Here only A is the limiting reactant. By default in the textbooks, we go with the limiting reactant A. Okay, it doesn't, I mean, please keep in mind, that means in the books it is structured in such a way, okay, always A is the limiting reactor. That is why you always get to see this equation in terms of XA. That means by default A is the limiting reactant they have taken. So what is the problem? And if one is the limiting reactant, another is not the limiting reactant, then where the problem comes? If you go with the limiting reactant, the things will be okay. If you go with the non-limiting reactant, you are wrong. And where exactly the wrong? I will show you today. Let us say there is a reactor, 4 molecules of A and 3 molecules of B. That means, I mean, the reaction is A gives rise to B. Don't worry. By looking at this, and always, I mean, A plus B, sorry, A plus B gives rise to C plus D. Okay. Now, see, both are my reactants. and by looking at itself you can able to find out the stoichiometry ratio and the amount of A and B here, and apply this formula, you get to know what is limiting reactant. Okay, let us. So Na0, number of moles of A before the reaction is 4, number of moles of B before the reaction is 3. After a certain time t, number of moles of A that is remained is 1, and number of moles of B that is remained is 0. That means all the molecules of B got consumed in the reaction. So let us define the conversion. XA is equal to Na0 minus Na by Na0, and 4 minus 1, that is initial moles minus final moles divided by initial moles is 0.75, that is 75% conversion. Similarly, if you apply the formula in terms of B, XB is equal to NB0 minus NB by NB0, that is 3 minus 0 by 3, 1, which is 100%. That means, now see whether my reaction got 75% conversion or 75% reaction happened or 100% reaction happened. So which one I have to take? Of course, obviously the one which consumes first in the reaction, you have to take that as a real conversion. Okay, that means reaction actually 100% happened. Here if you take the on the basis of a reaction is only 75%, and you can get a, why? Why we cannot take this? Because A is not getting A is remained here because B is not present here. If B would have been present here, this B and this A also got reacted. Okay, this B and A also got reacted to form C and D. Okay, but that is why you always you take on the basis of limiting reactant, which is in less in amount based on this formula. The thing is things would not get disappeared here. C and D has formed, CCC, DDD. Okay, and the thing is one molecule of A got remained, but we have to take on the basis of B. So hope you have learned something new about the conversion and the limiting reactant. Okay, thank you. We will meet you. I will meet you in the next lecture.